All right, today we are going to talk about how to find the area under a polar curve. But before we do, I'm going to show you something I don't want you to write down. I just want you to look at it. Okay, you'll see this graph right here. This is an old-fashioned curve that we used to find area under. Back in the day, before we learned what an integral was, how did we estimate area under a curve? What kind of shapes did we use? Rectangles, okay? So we would draw rectangles in here of different heights. Now usually our curves either went straight down or straight up, right? So we have another rectangle there, and we have another rectangle there, okay? 1, 2, 3, 6 rectangles. Pretty good estimate of the area of the curve, not the best. What could I do to make my estimate even better? Smaller intervals, which would mean more rectangles, right? So if I had 60 rectangles, it'd be a lot better than 6 rectangles, right? If I had 600 rectangles, that would be even better. So what we did is we eventually got to the place where we had an infinite number of rectangles under there, to where every rectangle was basically the width of my pen, right? And we started over here at A, and we went over here to B. We drew a bunch of lines, and it covered it in, and it perfectly filled the region we wanted to find the area of. Yes? Okay. Now, why did we make our rectangles this way? Well, partially because top minus bottom worked very well. And also, how is the distance to your curve measured? You go over and you go up, right? That's why it's up and down. It's a good measurement. Polar is a little bit different. Here is a polar curve. Do you remember that one from last year? Something that looks like that?
Yes.
Called a lemniscate. It's like a figure 8. But I want to find the area in this curve. The only problem is I can't do any sort of a top minus bottom because I'm constantly hitting the same curve, right? And that is actually not how this curve is generated. This curve is generated by going from here out. Remember that in polar, things are measured in a radius and an angle. So basically, this curve is generated by measuring how far out you go at a diagonal and how far up from the x-axis you are. Now, when we're talking about the area of this thing, instead of filling this thing with rectangles, which doesn't work, we are actually going to be filling this thing with, we take 2 of these and we go like that. We have a very, very skinny piece of pizza. Okay, I know it's almost lunchtime and thinking of pizza. You're like, I'm hungry. I'm sorry. We got to talk about pizza. Okay. If I did one giant piece of pizza and went like this, from say here to here, that fills in pretty good. Doesn't it do the whole thing pretty good? But if I put 2 or 3 pieces of pizza in there, it would fit even better. But if I could do 100 pieces of pizza, it'd be a lot. So what we're going to be talking about is pieces of pizza that are so skinny, they're as skinny as my pen, okay? And it starts going from here to here to here to here to here and going around. And basically, I'm going around the curve, okay? Filling it in and finding the area. Now, what is a real-world example of something that does something like this? There actually is one. And I'm going to go to a picture of it right now. As soon as I find Google. You know what that is? A sprinkler. Okay? Those long-distance straight sprinklers. Okay? The sprinkler head is at 0 at the origin. And as it sprinkles, it's going out in a straight line and covering the ground with grass until it hits until it either hits the ground or it hits a barrier. And I'm going to say that it's hitting a barrier of the edge of the curve. Are you following what I'm saying? So the sprinkler is starting here and it's going around and around and around and around and around. And as it hits the, I zoomed in and I didn't mean to. As it hits the edge, it covers that whole area with water. Agreed? So that is how we find the area of a polar curve. We think of it in terms of a sprinkler. All right, and that visual image really helps to make this make sense as we do the math that goes with it. Okay, so when you go back to here, think of these as the water that falls from the sprinkler straight down from when it hits, all the way around. Okay, this is how we calculate area in polar. So now let's go to the notes. Now, piece of pizza right here, agreed? Okay, we're making it a very fat one to start with. The formula for the area of that is a fraction of a full circle, yes? Okay, so the way they figure it is this formula right there. This is called the area of a sector of a circle, is 1/2 r squared times theta. And this is how they constructed the polar formula. Theta has to be measured in radians. And this is how they do the math behind it. So if this happened to be 3 units long, and this angle happens to be 30 degrees, you convert the 30 degrees to radians, which is pi over 6. So it's 1/2 the radians times the radius squared, giving you that answer right there. So the area of this is approximately 2.3 units, or square inches. Okay? So the next part of this goes into how they make Riemann sums, or shrink those pi pieces down to very thin ones. And so we come up to here, and here is our formula that's on the sheet. The area of the region bounded by the graph of R between the radial lines theta 1 and theta 2. So basically, where do I point the sprinkler when I start it? And then how far do I let it go until I stop it? That's theta 1 where it starts, theta 2 where it stops, measured off of the x-axis. The formula is right over here. That's the one we're going to use. 1/2 r squared d theta. Okay? Now, fifth period, I was very forgetful on putting the 1/2. Watch me, make sure I don't forget to put the 1/2 in front of our intervals as we do this. Okay? So let's take a sample problem. Graph and find the area of a rose curve given by this formula right here. R equals 4 sine 3 theta. So everybody needs to take your calculator. As soon as I find mine, where did it go? Oh, here it is. First thing you do, you are going to use your calculator to help you do some things. Some things you can do on the calculator, some things you have to do by hand. So everybody needs to be following along. Please make sure you're in polar mode, like this is right here. Make sure it's on POL in the mode. Go to y equals. And it says r's. We've done this already, right? Yes. So we're going to type in 4 sine 3 theta, close your parentheses. Theta is in the same place as x. Okay, we have to set our window, so don't push graph yet. Take a look at the grid that they gave us. It goes from about -4 to 4 in both directions. So as far as the window goes, theta, unless they tell you otherwise, needs to be 0 to 2 pi. Now, if yours already says 0 to 6.28, you're good. Okay? But I need everybody to change your theta step to 0.05. Change it to 0.05, please, because it makes the graph draw at a very good speed so you could follow what's happening. Okay? Now, my x min and max are way off, so -4 to +4 with a scale of 1, and then -4 to +4 with a scale of 1. After you've typed that in, push graph, please. And watch it as it graphs, please. Looks like a propeller, right? Now, I noticed something on this graph that doesn't usually happen. Did anybody notice anything kind of weird happen when it graphed? It did what? Right. But it also traced over itself more than once. Did you see that? If you did not see that, or even if you want to see something happen again, go back to the equation and type over the first character with what's already there. That resets the graph. and then you can see it happen again. So this time, watch it very carefully. It's going to trace out all three of them, and then it's going to trace them again. So watch it do it. Around, around, around. Oh, there it goes again. Around again, and around again. Okay, so it makes it look a little darker. Okay, I want to find the area of all three of those. Question number 1. Do they look like they're all the same size? No. No, they don't. But that may be distorted from the fact that the screen is rectangular. We talked yesterday about how to make the screen square. Do you remember what to push? Zoom 5. So go up to Zoom and press number 5. Now look at the... Now do they look to be the same size?
No. I don't think so.
Okay, my screen is slightly distorted, but they are actually the same size. Yes, sir?
Is it supposed to start from the right?
Yes, because it starts when time equals 0. And at time equals 0, it's going around this way. Okay? Now, the fact that they're all the same size is going to make life simple because of the fact that I can do the area of just one of them and multiply it by 3, and then I get the area of all of them. Yes? Less work. We always like less work, right? Because otherwise you'd have to build 3 separate integrals, and you don't want to do that. Now the question is, where does it start doing this one, and where does it stop before it jumps to the other one? I need to know that. The only way you can find that is by hand. So we have to actually do the math to find out when it's finished sprinkling through the first petal and scoots over to the second one. Now, it starts at the center. What is R at the center of this graph? It is 0. So we want to set our equation equal to 0 to find out what t values, or we're going to set our theta values we're going to set the window for. So step 1. Set R equal to 0 to find limits of integration. On almost all of these problems, you have to set either 2 equations equal to each other or an equation equal to 0. So 4 sine 3 theta equals 0. How do I solve this? What do I do first? Divide by 4. So sine of 3 theta equals 0. Okay, some of you saw me do this question yesterday. Some of you did not because we got cut short on time. We're going to do one exactly like it. So when you have more than just a theta in here, you keep it all as one thing for the next step. You pretend like it's a single theta. And you ask yourself, where on the unit circle does sine equal 0? Where does just sine equal 0? Don't worry about the fact that there's a 3 there. At 0?
Yeah, 0.
0? Is it sine equal 0 there? Yes. And then again at pi. Question?
Sorry, I think I missed it, but where did the 4 go?
I divided both sides by 4 in my head. Okay? 0 and pi. That is correct. But this 3 tells me I must go around the circle 3 times to get all my answers. So if I go around again,
360.
which is what in radians? 2 pi. You are right. What is the next stop going to be? 3 pi, right? 0, 1 pi, 2 pi, 3 pi. What's the next stop? 4 pi. We're going on a merry-go-round, right? And what's the next stop? 5 pi. That's far enough. Okay? Now that I've gone around 3 times, how do I solve for theta? How do I get the 3 off the theta? Divide by 3. The reason I have to go around 3 times is because if I don't, I'm not going to get all the answers. So now we just divide both sides by 3 and we get theta equals 0 over 3, which is 0, pi over 3, 2 pi over 3, then pi, then 4 pi over 3, and 5 pi over 3. those are all the places where the radius is 0. Now, we never sketched this thing. Let's stop and do that real quick. This thing goes down to -4. Draw that petal first. And the other two come out kind of at a diagonal in this quadrant. Do the best you can. Doesn't have to be perfect. Mine are definitely not perfect. Yuck. Let's try that one again. Now, I didn't draw it the way the calculator draws it in the same order. But if you think about it, if you're going to trace that thing with your pencil, how many times are you going to hit the center? You're going to start at the center 1, 2, 3, and then when it traced around again, it hit it for the 4th time, the 5th time, and then the 6th time. So tracing it twice makes it hit 6 times. Okay? Now my question is, would it work to give me only one of the petals if I only picked 2 of those? If I picked the first 2, would that complete one whole flower petal? We're going to test it and see, because if it does, those are the limits of integration I want. So does 0 to pi over 3 make this whole thing just once? So here's what I want you to do. Once you think you know what your limits are, what you do is you test it in your calculator. So please go to your window and change your limits of integration to 0 to pi over 3. Change to go from 0 to pi over 3 only, and see if it'll draw just one petal. Because if it will, that's the limits I need for my integral. Push your graph. Okay. Pretty much it's getting back there, but it's not exact. It's close. And it actually, because we know that's where it equals 0, that is the correct answer. It did go all the way around. Okay? So, these right here are the limits for the first petal. Those are the limits for the first petal. And that's all I need, because I'm just going to find the area of one petal and divide it by and multiply it by 3. It's not considered negative, because it's all area is considered how much ground you cover with your sprinkler. And all of it is covered no matter which direction you're going, so it's not considered negative. That's a good point. So to do this problem, we now write that the area is equal to 1/2 the integral from 0 to pi over 3, because that's what made the petal on the calculator. The formula says r squared, so we write 4 sine 3 theta in a parentheses squared d theta, and that's what we're going to type in the calculator. Or, just like when we used to do things with y1s and y2s, we can actually do the same thing with r's. You may be able to type this in the calculator. I'm going to put this in a parentheses. You're going to put in r1 squared d theta, and I'm going to show you how to do that. This is the calculator. That's what's going to go in the calculator. You can type in exactly the way it's written above it into the calculator, but as the problems get more complex, it's a lot easier to use the R1 and the R2. Okay, I'm going to scoot this to the left so I can put my calculator down here. Can you, oh, you can't even see that. Can you see that? Kind of. Can you see that? That's a little better. Okay, so I'm going to type in 0.5, math 9, 0 to pi over 3. Now, if you're going to type it in like the top line, you have to put another parentheses in here for your, not there, you in here you'll have to put another parentheses for your 4 sine 3 theta. If you're going to do the r's, you don't have to. If you want to do the r's, you push to get the r what you used to push to get y1. What are the buttons you push to get y1? Alpha and trace, and there's r1. Do you see that? We already put the equation in r1, so put r1 and then push the x squared key, d theta. Now when you push the x, it'll give you the theta like it needs to be. Okay? Push enter, and there's your area. Now, is that the area of the whole flower? No, that is the area of what fraction of the flower? A third of the flower. So I'm going to write that this equals 4.189, and what am I supposed to do to this? Multiply by 3, and I get 12.566. And there's my answer. Please turn the page. The next two problems, I can pretty well guarantee you will see on the AP exam something like it. Lights off. There we go. All right. They like to ask questions about outer and inner loops and about on polar graphs laying on top of each other. So let's take a look at this. Find the area of the region lying between the inner and outer loops of the limacon y equals 2 sine theta minus 1. So this is all one graph, but it loops over itself in the center. But they only want to find the area of the shaded part. Okay? So what we're going to do first is we're going to graph this on the calculator to kind of see what direction it goes, where it starts, etc. So turn your calculator on, go to y equals, type in 2 sine theta, close that parentheses, minus 1. Actually, that's better right there. Now the screen, what does it say? Negative 2 to 2. This will work. Let's just leave it where it is. No, we got to set our window. We got to set our thetas. We want a whole curve, and a whole curve is 2 pi. So 0 and 2 pi right here. Always leave the t-step alone. Leave it at 0.05. It's a good speed.
So like for all of the graphs,
For all of the graphs, leave it at 0.05. Okay, I'm going to push graph. Just watch the way it draws itself. So it starts and does the first loop, then it goes up and does the top and comes back around. Okay? All right. Now, I could start farther down the road and I would eventually get all the way around, but this one starts in the middle, then does its loop around. So let's think about watering this thing with a sprinkler. Okay? I'm going to think of it a little bit differently, so let's blow it up kind of big. I'm going to start at 0, and I'm going to water starting to the left. So as I water this thing, I'm not going to cover it completely, as I start going around, do you notice that I am watering both the shaded and the unshaded part? Yes? Continue around. I'll make it a little wider. So, but then what does the graph do? It goes around and then it goes into the loop. So basically, the loop is going to get watered twice. Do you see that? Okay, so if you go around and having it water it like that, it's going to water the center twice. And the center is what I don't want the area of. Okay? So, if I had a giant flamethrower that was like an unwaterer, I would have to go over this section twice because it's double wet. Are you seeing what I'm saying? So in order to get the area of this, I have to do the whole thing and subtract off the center twice. Are you following what I'm saying? I can't subtract it off once. It's not going to be enough. I've got to subtract it off twice. Yes? Okay, let me see if I can say it again. I'm actually going to change from this to this. Oh, that's really fat. Let's change it to a different level. Oh, because that's not going to work like I thought. I'm going to have to do it this way. Getting to every point involves going from the center out. This is how we measure around a curve. And now, if I was a sprinkler watering this thing, I would cover the entire graph, including the center, because the water is going to spray all the way out to here. So even if I go just around the outside, I will have covered the entire graph. But after going around the outside, I've got to go through the inside also. And when I go through the inside, I'm watering the inside again. Okay? So in order to get the area of the shaded part, I got to do the whole thing around and then subtract off the center twice. Okay? So, let me erase this. Hello, wake up. There we go. So I'm going to write that in notes to myself. It is the area of the entire region minus 2 times the area of the inner loop. So that's basically what I've come up with for this graph. I'm going to do the area of the whole thing, 0 to 2 pi all the way around, minus the area, double the area of the inner loop. Okay, now, the question is, where does the inner loop start and stop? And notice that it starts and stops at 0. So I've got to find out how far around the thing is it when that happens. So once again, we've got to take and set r equal to 0. So 2 sine theta minus 1 equals 0. This is a little bit easier than the last one. Can you solve for theta? So 2 sine theta equals 1. Sine theta equals 1/2. All right, now we got to think unit circle again. I know it's not everybody's favorite thing to do. Question 1. My sign has to be positive. Where on the unit circle is sign positive? Well, I know it's quadrant 1 and 2. Okay? Now the sign is the y. Where is the y 1/2? Pi thirds, pi fourths, or pi over 6? Pi 6. It's the shortest one, which is pi 6. So theta is pi over 6. And then the other one's over here. That's 5 pi over 6. Okay? So I only got 2 answers, and that's good, because hopefully those are my limits of integration. So what I'm going to do is I'm going to test my theory. I'm going to test and see if I set my calculator to only these 2, is it going to graph just the inner loop? So take your calculator and let's test it. We've already got it in y equals. Go to the window and set your T-min to pi over 6. Just type over the old one. And set your T-max to 5 pi over 6. Did I say T? I meant theta. Thank you. Theta min and theta max. Theta min is pi over 6. Theta max is 5 pi over 6. Now, if I'm right, those 2 should make me graph just the loop. Okay? Let's see. Push graph. Is that what it did? Did it graph just the inner loop?
Yeah.
Yes, it did. So I'm right. That's what I need for my limits of integration to be for the loop. The entire graph's easy. The entire graph is 0 to 2 pi. The inner loop is just pi over 6 to 5 pi over 6. So I now know how to set this up. Okay, so put the calculator aside. All right, light off. The area is going to be 1/2 of the whole thing. Now, what did I just tell you the limits of integration are for the whole thing all the way around? 0 to 2 pi. And
Okay. So why would we?
okay, remember we're doing the area of the whole thing minus 2 times the area of the inner loop. The inner loop is from pi over 6 to 5 pi over 6. The whole thing is from 0 to 2 pi. Okay? So it's going to be r1 squared d theta. That's the whole thing. And we're going to subtract off 2 times 1/2 integral. What are my limits for this one? Pi 6 to 5 pi over 6. r1 squared d theta. If you do the r1 squared, that's what you're always going to put on the inside, if there's only one equation. Okay? Now, just like before, you need to go up here and tell me that's r1. I went up to the top and said that r1 equals the curve. And you can write it that way. Okay, I'm going to scoot this up, and then I'm going to put the calculator underneath it so I can type it in. So clear, math 9. Oops, what did I forget? Got to do the 0.5 first. 0.5 math 9, 0 to 2 pi. Alpha trace to get R1 squared d theta minus. Now, I really don't have to put in the 2 and the 1/2 because they're going to cancel each other out anyway. If you want to put them in, you can, but you don't have to. I'm just going to do my math 9 without it. Then the pi over 6 to 5 pi over 6 R1 squared d theta. When you push enter, if you typed it in correctly, you should get this. A equals 8.338, and that's the area of the shaded part. A question was asked during my other class, which I think is good to mention on video. Do they want units on these? And the answer is 99% of the time the answer is no. Unless the problem specifically addresses units like square inches or square meters or anything like that, don't worry about units. Just put the answer, okay? No units necessary. How we doing? Doing okay? All right. So, any questions? Are we good? Okay. Now let's look at the next question. This is one that they like a lot. I think last year's AP test on the BC had this on there, something like this. Find the area that is inside this curve and outside the circle. So it's pretty obvious on here which one's the circle and which one's the other one. Can you see the line for the cardioid underneath it? Okay. Now, if I'm going to do inside the cardioid, if I sprinkled all the way around the cardioid, I'm going to get cardioid and circle, right? Okay. Now, I was getting a little sloppy right through here. Let me fix this. If I go all the way around the cardioid, I'm going to get that right there. Now, if I subtract off the circle would, there's some part of the circle that's not even in the cardioid. Do you agree with that? Okay. So what really matters is this part. If I only went from here, let me just do this again. I hate it when I change pages. There we go. If I only go from here, as I erase, here to here, all of the cardioid, and then subtract off the circle, that would give me what I want, wouldn't it? Yeah. If I only did, no, I went too far on this last one. Okay, I would only go inside the lines. So what I want to do is I need to find where these two graphs cross. I want to make my calculator draw just that. Not the whole thing, but just that. If I can do that, I can find the area properly, okay? The question is, where is this point and where is that point? Okay, calculator does not have an intersect feature, so we have to do it by hand. So what we're going to do, if you want to find the intersection of two equations, what do you think you're going to do to their equations? Set them equal to each other, exactly. So, first thing we do, we set the equations equal to each other. To find the intersect. Find the intersection. That's what we're going to do first. So 3 plus 2 sine theta equals 2. Do the math. I just noticed I was off screen. There we go. Okay. Move the 3 over. We get negative 1. Now actually, they made our life easy for us. This time it says sine of theta equals negative 1/2. In the last problem, we found where sine of theta equals positive 1/2. So all we got to do is just look at the graph and on the bottom and see where those are. Let me show you what I mean. Come up here. When we did sine of theta equals 1/2, we looked at the picture and we said, oh, that's this point here and this point here. So sine is going to be negative at the ones below the x-axis. So we're talking about this one here and this one there, right? This is over 6, this is over 6, because the other ones were over 6.
11.
Which one's 11, the left or the right?
I think it's
The right one. Does anybody know what the other one is? This one's 7. Good. Okay? So, our theory is that this one over here is 7 pi over 6, and this one over here is 11 pi over 6. Okay? So, if our theory is correct, let me write this down over here. 7 pi over 6, 11 pi over 6. If our theory is correct, if we put those in as the limits of integration, we should get the graph we want. Okay? So let's test it. Now you may be thinking, Miss Bell, I know it's going to work. Why are you making me do this? Guess what? It's not going to work. It's not going to work. Let me show you. So we set our window to 7 pi over 6, 11 pi over 6. Okay? Let's see what happens. Now, I still have my graph on simultaneous mode where the graphs graph at the same time. If yours don't, that's okay, because you'll see it anyway. Did I change my equation? No, I forgot to do that. Oops. Go to r equals 3 plus 2 sine theta, and r2 is 2. I need to label these. This is r1. This is r2. Now push graph as soon as you type those in. Am I graphing the top part of the circle? Nope. I'm graphing the bottom. I don't want the bottom. The bottom's the part I don't want. Yes?
I only got the top one.
Okay, did you put 2 into the R2? Push. That's why. Okay, my little smiley face there is not what I want. I want the rest of the graph. Okay, so what I have to do is I have to rename one of these. So going from 7 to 11 gives me the bottom. So I need to call this one here not 11. I need to give it its negative name. What is its negative name right there? What angle is that? Negative pi over 6. So let's try that. Give it a different name and see if that makes it work. So we want to see if that going from negative pi over 6 to 7 pi over 6, you have to go in order from smallest to biggest, is going to work instead. So let's see. Let's scoot that up a little. So what if I change it to negative pi over 6 to 7 pi over 6 and push graph? Looky there. Negative pi over 6 for theta min, 7 pi over 6 for theta max. And I got, who's that character on Mario with the hat that looks like this with all the polka dots on it?
No, the mushroom man.
The mushroom guy. Toad, that's right. Yoshi and Toad. Looks like Toad's hat, right? Isn't that what I want the area of? Okay. Now, I mentioned earlier, and I'm going to mention it again. Regular graphs for area, top minus bottom, or right minus left. For polar, it's outer minus inner. So the outer curve is R1. The inner curve is the circle, R2. And remember, we're doing it from here out. And if you do outer minus inner, you're going to get just that right there. Yes, ma'am? Okay. What I did is when I first graphed it with 11 pi over 6, I found I graphed the wrong part. So I came up with a different name for it. I decided to do, instead of going around the circle this way, I said, well, let me go backwards instead. And then I said, oh, it's negative pi over 6. Okay? All right, so now we're ready to do this. The area equals 1/2 limits of integration are what? Negative what? Pi over 6 to what? 7 pi over 6. R1 squared minus R2 squared d theta. Remember, it's outer minus inner. Because they start and stop in the same location, it's just outer squared minus inner squared. Kind of like when we did washers. Remember big R squared minus little r squared? Same concept. Okay? So try typing that in, please, as soon as you write it down. Okay. So here we go. 0.5, Math 9. Now, if you're like me and you forget to put in the 0.5, you can just do it at the end. Just multiply your answer by 0.5. Alpha trace R1 squared, put the pencil down, minus alpha trace R2 squared d theta. Boom. And that should be what you get right there. 24.187. Okay. Questions? Are we good? Okay. Next problem. These are the same two curves, but in this case, I want this shaded part. They will never give you a sentence like this without a picture to go with it. There's no guesswork. You know which area they're talking about, okay? So they will give you something like that. Now, if you're doing this part right here from these lines, let's make this bigger. Okay, if we start here, if I want to sprinkle this in the shaded part only, which equation am I going to stop at? The circle or the cardioid? I only want the sprinkler to go out over the shaded part. Which curve am I hitting? I'm hitting the circle. I'm stopping at the circle, right? So if I start here and start going around, I'm hitting only the circle until I get to here. Now, if I keep going, am I still hitting, if I'm doing just the shaded part, am I still doing the circle? No, this is the bottom of the cardioid. Are you seeing what I'm doing? Let me do a different color. From here to here, let's do this. Different. There we go. From here to here, my sprinkler is only hitting cardioid. Do you see that? Above it, it's hitting circle in order to cover the shaded part. Now, I could do one minus the other, but this is a lot faster. It's just cover the circle on top, cover the cardioid on the bottom. That's what I'm telling the sprinkler to do. Okay? Now, if I start here and stop here, and I want to go this way and get the top part, do I call this negative pi over 6? Or do I call it 11 pi over 6? If I want to start here and go this way, I call it negative pi over 6. So I'm going to do the circle from negative pi over 6 to 7 pi over 6, just like I did before. Okay? And then I'm going to do the cardioid from 7 pi over 6. You can't see. I'm doing, oh, too high. I'm doing the cardioid from 7 pi over 6 to negative pi over 6? No. To where? 11 pi over 6. Since I'm going all the way around, for the second part, I'm going to call it 11 pi over 6. So from negative pi over 6 to 7 pi over 6, I'm hitting the circle. And then from 7 pi over 6 to 11 pi over 6, I'm hitting the cardioid. So that's how I set it up. Okay? So I'm going to move back over here. Make it smaller. That's too small. Boy, it's amazing how how small I can write when I blow it up. So the area, you can't see now. Move over there. Thank you. Please tell me these things because I can't tell from where I'm looking. Okay, now you still can't see. Well, there we go. Now we can see everything. If I go up, there. Okay, so we're going to do from negative pi over 6 to 7 pi over 6, the circle's equation. Which one is the circle's equation? R2 or R1? R2. R2 squared d theta. That's what I was about to ask. Did I forget something? I forgot the 1/2, so throw it in the front. Or inside, it does not matter. Plus 1/2. The next piece goes from 7 pi over 6 to 11 pi over 6. Of which equation this time? R1. R1 squared d theta. Okay? In the interest of time, I'm not going to make you type it in the calculator. I'm just going to tell you what the answer is. And you can go home and type it in later to double check yourself. It is 10.370. Look up here at the top. It says, because a polar point can be represented in more than one way, you have to be careful when you find intersections. So, I want to know where this curve and this curve cross each other. So what am I going to do to their equations? Set them equal to each other. 2 minus 4 cosine theta equals 2. Do the math. Move the 2 over. Negative 4 cosine theta equals what? 0. Divide by negative 4. Cosine theta is still 0. Where does cosine equal 0?
At 0. No, sorry. Pi halves.
Pi halves
3 pi halves.
and 3 pi halves. Now, this is only going around once, so that's all the answers that I have. Agreed? How many crossing points do you see between that curve and that dotted circle? I see 3. How many answers did I get? I only got 2. Wait a minute, what's going on here? Sometimes this happens. I'm supposed to have 3 answers, not just 2. Okay? So, where's the third answer hiding? The third answer is hiding in the fact that the circle r equals 2 and the circle r equals negative 2 are the same circle. Because remember, when we plotted points yesterday, any point here could be written as 2 comma something, or it could be written as negative 2 comma something. Didn't we do that? We wrote 2 with a positive and 2 with a negative?
Yeah.
Yes. So, those points are on the same circle. So what we do is if you're missing a crossing point, go back and set your equation equal to negative 2. Only if you're missing a point. If you need an extra crossing point and you didn't get them all, this is what you do. Now subtract 2 from both sides. Negative 4 cosine theta equals negative 4 cosine theta equals positive 1. Where does cosine equal 1?
At 0.
At 0. Not at pi. At pi it's negative 1. The only next one would be 2 pi, and that's too far. There's my missing answer. This is the third answer. That's the big important thing. Set it equal to the negative if you're missing answers. Okay? Questions on that? Okay. I have enough to get started on the next problem. What I'm going to end up doing, mark this out, we're not going to do that. Okay? Can I move this up? Okay. At the bottom of the page, it shows the math that they go from to do the parametric arc length, which is what we did last class, or 2 classes ago, to the polar arc length, which is here, which is the started to right here. They show the math of how they got there. We're not going to go through all the steps. I want to jump straight over to the formula, which is at the top of the back of the page. So either circle or highlight this formula here. We already wrote it on the flip book. The arc length of a polar curve is the integral from, what are these goofy letters here? Do you recognize those letters? This is alpha, and this is beta. By the time you finish college math, you will know all your Greek letters, because you're going to see them all over the place. But notice that it's r squared plus the derivative squared in a square root sign. So look at number 8. The arithmetic spiral given by r equals theta, and the logarithmic spiral is given by r equals e to the theta over pi are shown in the figure below. Find the difference in their lengths from 0 to 2 pi. How much longer is one than the other? So we have to do them one at a time. So we're going to call this one 1 and this one 2, and we're going to do each one individually. So we're going to find the length of 1 first. Now, in order to find the length of 1, we need r squared and we need dr d theta squared. So let's write down what we've got. It says r equals theta. My question to you is, what is dr d theta? It is 1. It is 1. Okay? If that's kind of confusing to you, think of it this way. Change r and theta to y and x. If y equals x, what is dy dx?
dx.
Is dy dx is just 1, right? Or dx dx, which is 1. Exactly. So there we go. There's our 2 components that we need. So our length L is going to be the integral, and it told us to go from 0 to 2 pi of the square root of r, which is theta squared, plus its derivative squared. I shouldn't have made that quite so long. Let's fix that, because I need room for my d theta, which does not go under the square root sign. So type that in the calculator and see what you get. Now there's no 1/2 in front of these. These are just straight integrals. 0 to 2 pi. Make sure you put your square root in, because I keep forgetting. Theta squared plus 1 squared d theta. And I get L equals 21.256 for the standard arithmetic spiral. Okay? Now we're going to do the other one, which is a little trickier because of the way it's written. So, number 2, my formula is r equals e to the theta over pi. Now the question is, what's the derivative of that? Copy paste. Very good. So e to the theta over pi times the derivative of the exponent. And it is 1 over pi. We did one the other day that had a t over pi in it. Y'all remember that? And we figured out that it was 1 over pi. So times 1 over pi. There we go. You could put the whole thing over pi instead. Yes. So our L is equal to our integral, 0 to 2 pi. square root sign, because I forgot first period to put square root sign on this one. So parentheses e to the theta over pi squared plus, since this is times 1 over pi, I'm just going to put it over pi. So e to the theta over pi, all over pi, in a parentheses squared, like so, d theta. Take a look at that. All right, let's type this little guy in. There it is. So we get 21.064. Pretty close to the other one, which I figured they would be considering the drawing. They're almost the same size. Okay, so did I answer the question they asked? No. What do I need to do to these two values? Subtract them. So 21.256 minus 21.064 is 0.192. That's my difference. I'm not doing number 9. I ran into it, so don't worry about it running over in that area as well. All right, mark out the bottom half of this page because that is surface area of revolution. We are not doing that. That's always a good feeling to say, yes, I don't have to learn that. Not now, maybe in college. It's up to your professors. And we are done for today.